Thank you. So I am the Senior Director of Developer Relations at Flurry. I joined Flurry about 3 years ago as the 19th employee, about the 9th engineer. So I've been able to program across our entire stack during that time. I led SDK development at Flurry for about 2 years. My team still owns the API. Most importantly, we are the engineering team that gets to work directly with developers that are our partners and help them integrate our solutions. So if there's any problem in the system, regardless of what product it is in, we investigate, even if it's SDK all the way down to HBase. So a little bit about Flurry. We are the #1 mobile app analytics provider. We see 1.2 billion devices per month. We are used by about 400,000 applications across 125,000 different companies. And we see a lot of data. So 1.3 trillion monthly events, 4 billion sessions per day. We have the #2 ad network. And the monthly conversions we see are about 130 million, which includes app installs as well as completed video views. To the right, you'll see some of our partners. These are some of the biggest companies in mobile that trust Flurry as partners and use some of our services. In that regard, I am happy to announce that Flurry is now integrated with the T-Store. So Flurry was very honored to be able to partner with the leading app store in Korea, one of the most advanced mobile markets in the world. The sign-up is very easy. It's free. Just go to your T-Store developer account, click on the Flurry link, and from there you can actually create a Flurry account within the T-Store Developer Center. If you already have a Flurry account, you can just associate that with your T-Store account. And then from one place, you can log in and see your analytics data in the T-Store Developer account. So we know it's important to be able to access your data from a central place, so we were very happy to be able to bring this to you with our partnership with SK Planet. So a little bit about our products. The foundation of everything we do is analytics. I told you the scale that we support on that. That data really powers our other products. So for our advertisers that want to acquire great users, that data goes into our App Circle product because we want to deliver you the best user that we think will perform the best within your app. We have about 10,000 applications that use App Circle right now. For our publishers, we have AppSpot. This is a complete ad-serving platform, whether you are doing direct deals with different companies, whether you are mediating different networks like iAd or AdMob. And finally, our real-time marketplace for RTB. And so we have about 7.5 billion impressions a month going through that. And so all in all the data that flows through Flurry's system, we see about 1.9 terabytes of data per day, which is a lot of data. So today we'll be discussing how we got to this path of real-time processing while we switched from our pure MapReduce framework to a mixed framework. We still use MapReduce. It's great for a lot of reasons, and we will always use it. But we will discuss how we're using Kafka now in our process. We'll talk about how we tuned Kafka to work very well in our environment, and finally, how we handle errors. So I want to start with the end, why we did this. What you're seeing now is a graph that monitors basically how long from the time we get a report from a device till it gets processed in the first part of our system. And so these are in seconds. So just over 5 minutes, 300 seconds to 384, we're able to process that piece of data. Before, with our MapReduce framework, it was taking 2 to 4 hours to process the same data. So 5 minutes was a big improvement over our previous MapReduce framework. So here was our previous model. And it's a standard MapReduce framework where we get a bunch of reports from devices. Those are collected in various web servers, stored within HDFS, and then we run MapReduce jobs over that. The results we store in HBase, or we take some external action like alerting a developer. a deeper look into this MapReduce framework, you'll see the phone that generates data over a binary protocol to Flurry. Our agent portal collects those logs. Agent portals run on Jetty. That gets stored in our raw data log archive, HDFS. And then that gets processed by our data log processor, and that's a MapReduce job. And this is the part where we focused the improvement. I mentioned that this was very important to me because if a developer is integrating, one of the key things to know is it working? You know, if I'm sending events, if I've integrated with Flurry for the first time, if I'm upgrading a version. And this is the part of the process where if you look at your event logs, the raw data on the Flurry dev portal, you will see data now within 5 minutes. Before, it would take 2 to 4 hours to actually see that you've integrated successfully. So for our developers, this is a huge improvement and a big reason why we went to Kafka. The rest of the process, the data log processor normalizes the data. It does data integrity checks, and then it stores the resulting data in HBase. And then we run another series of MapReduce jobs called the metrics computer, and that information is stored in our metrics table in OLAP cubes. And that makes it very fast for you to log into the developer portal and see data in various ways. So there are a lot of good things about MapReduce. Like I said, we still use it. We plan to continue using it. It's worked very well for us. The first picture over here, it's very easy to break up your logic into distinct jobs and run them independently over the cluster. And so different teams can develop their own jobs using the same data and not worry about dependencies with other teams. The top picture, it's scaled very well. When we took this picture, we were doing about 25,000 connections per second. It's increased a lot even since then, but it's scaled well for us. We can handle this 1.9 terabytes of data a day, and our systems stay up and they run smoothly most of the time. With Hadoop, you have a great administration framework. You can pause jobs. You can increase the priority of them. You can kill them if need be. And we have several counters, so you can actually see the progress of jobs as they are computing. So you can see if something is going wrong while the job is running and it needs further administration. So these are all great things about the MapReduce framework and how we use it. There are some bad points for us, particularly in how we use it. With the previous data log processor, we had an indirect dependency. We would basically batch up a lot of records, and then we would process those in the data log processor. So we would process about 500 million records in one job, and the job would go for about 2 to 4 hours, and as soon as the job finished, we'd start another job. There was also a penalty for that because a job has a start and it has an end. During the start, you're loading up data that you need to run the job. During the end, you clean it up. So during the startup time, we actually have to load a lot of in-memory objects because when you're processing through 500 million records, you want to do it as fast as possible. And so pulling from MySQL or even Memcache was too slow. So we put a lot of objects in memory, but we pay a startup penalty for that. So now about why we went to Kafka and how we did that. First, Kafka is a high-volume messaging system. It can support hundreds of megabytes of writes from producers, from thousands of producers to a single broker with no problem. The work for Kafka actually came out of LinkedIn. They were using it to monitor their activity streams and operational metrics. They wrote a white paper in November 2010 introducing it. It was proposed for incubation in Apache in June of 2011, quickly accepted a few days later, and became a top-level project in November of 2012. So this is still a very young project. I mean, it's been 3 years since the first paper came out about it, but it's had tremendous adoption. A lot of big companies use it. Foursquare uses it. Netflix is another company that uses it. Twitter, if you're familiar with the Storm framework, a lot of their real-time processing is built on Kafka. So it's gotten great support from the community and a lot of use. So Kafka is a basic producer-consumer setup. producers will send their messages to a topic. A topic is basically just a category of messages. So for LinkedIn, a topic might be operational metrics, and another topic might be the activity stream. The broker's responsibility is just to store the data. It's to store the data and make it available for the consumer. The producers push data to the broker, and the consumers are actually responsible for pulling that data and managing how much data they pull. This is the offset into the data. So the Kafka broker is not responsible for keeping track of all of the consumers. The consumers do that independently, which really helps for scale. A deeper look into the broker. A single topic can be split among many partitions. The only rule for a partition is it must fit completely on a server, but you can have thousands of partitions for a single topic. The partitions are an immutable write-ahead log. Data comes in and it just gets appended on the back. And these numbers are just offsets into the log. And so if a consumer says on partition 0, I'm at 6, you know they've read 0 through 5. We're going to talk about a couple of abstractions that Kafka builds on top of this. This is key to how it's scaled and set up. So the producers will send data we showed in the previous slide to a broker, but Kafka has the notion of a cluster. And a cluster is multiple brokers that producers will send data to. In this example, we have 2 brokers with 4 partitions. Remember, a topic can have as many partitions as it wants. So this would be an example of one topic. Broker 1 has partition 0 and partitions 2. Broker 2 has partitions 1 and 3. And then finally, you have the concept of a consumer group. So a consumer group is just a logical collection of physical consumers. We have 3 physical consumers in this example, 1, 2, and 3. And to the broker, these all look like one consumer. And so you will ensure that all data is read from these from the available partitions. Another thing, there are 2 things to note here in the setup. Kafka makes heavy use of Zookeeper. If you're not familiar with Zookeeper, it's a distributed coordination system. It's how systems in this distributed system, kind of say, hey, I'm alive, I'm in this group, and they can store data that is available to the entire cluster. And so producers don't actually write directly to the brokers in Kafka. They actually write directly to the partitions wherever they live. And they do this through Zookeeper through a concept called the partitioner. And so the producer, if you don't have a partitioner, the default is a random partition. But if you were developing something in production, you don't want to use the default. What Flurry uses for the partitioning algorithm is essentially give the data to the partition that is progressing the fastest. So if you have a consumer that is slow, and it's not progressing, you don't want to give them more data. So we basically give the data to the partition that is owned by the consumer moving the fastest. In regards to the consumers, one important invariant in Kafka is a partition can only be owned by a single consumer. This is how they provide a lot of ordering guarantees and how they handle recovery. So in this example, you'll see partition 0 is owned by consumer 1. Consumer 2, on the other hand, owns 2 partitions, partition 2 and partition 1, and that's okay. But what you can't have is a partition owned by multiple consumers. If you had 5 consumers, you would be guaranteed that one consumer would never receive messages. So there's never a reason to have more consumers than partitions. However, if I were to add another consumer to this group, it is likely that P2 or P1 would be assigned to the new consumer. So the reasons we really wanted to do this is we wanted to do smaller batches instead of these 2 to 4 hour batches, and we wanted to increase the number we could run at once. As I talked about before, after this Kafka process runs, there's data available immediately to our developers and our partners, and that was important for us. It's also available to the MapReduce jobs quicker. So the MapReduce jobs are independent. There's not a hard dependency on the previous data log processor, but the fact is, if it takes 5 minutes for a report to come in from a device until it's available, then that's a lot quicker than 2 to 4 hours. Even though there's not a hard dependency, there's one there. The other great thing about Kafka is it runs forever. It's not a start and end like jobs. So the startup time is greatly amortized over the life because you only pay that small penalty once, and then the consumers are just up and running. The last thing that was important for us, we have a very large Hadoop and HBase infrastructure. And so we wanted to bring in something that fit within our infrastructure. And so we use Zookeeper a ton, and our admins know how to administer it. And Apache Kafka was built on that as well. It also had built-in consumer logic for Hadoop, which was also important to us. So, introducing the data log consumer. That's the area in yellow. We replaced the HDFS data log archive and the data log processor with this data log consumer. You'll see in the picture, it's Kafka and HDFS underneath. Kafka does not rely on HDFS. We are using HDFS because we are using version 0.7 of Kafka. That version is the latest GA version, but it did not support replication. Version 0.8, and if you went to the Kafka site, you would say, of course, it supports it because version 0.8 does have replication. However, that is in beta, and while it looks pretty good, we want to wait until it's GA. So basically what we do is we store data for about 3-minute time periods into HDFS and then roll that over and produce it to our brokers. The rest of the process is the same. So Kafka's been very, very good for us. It's been a very stable service. It did exactly what we thought it would do in terms of decreasing the time it took to process data. But of course, whenever you bring in a new system and put it right at the front of your process, there will be some challenges. So the first challenge we saw were Zookeeper timeouts in our consumers. Our consumers in these in-memory caches use a ton of memory. And Kafka did not account for the basically garbage collection pauses that would occur while the data logs were being processed. And so randomly, our consumers would start to die because Zookeeper thought they were not alive anymore. And so all we had to do was just increase the timeout once we realized what was occurring. When you're scaling, you definitely want everything to be async as much as possible. And Kafka, in its part, is mostly async. The one part we found that was synchronous was when the producers are starting up and connecting to Zookeeper. And so during that time, that's a synchronous connection, and we were seeing some blocking. And so we basically wrote a wrapper that would control that in an asynchronous fashion. The next thing is we had to disable the default commit interval. So in our log records, we have several types of logs that we track. We track agent reports from phones, we track ad logs, we track tracking server and budget updates. So all of these are different types of logs, but the agent reports for analytics can be very large because what we do is we take a bunch of records and put it into one log that helps processing it quicker. But those can take about 2 to 3 minutes to process. And so what would happen is the default commit interval was 60 seconds. And so it would commit the offset in the consumer while we were midway through processing a log. And so we didn't want to actually commit data when we hadn't processed the full log. So we said, we'll control ourselves, and every 1,000 logs that we process in production, we'll do a commit at that point. And that worked very well until we quickly realized it doesn't work very well on a dev machine, because the developer is probably producing a couple of logs unless they're load testing, and the data would never progress and commit. So we actually had to write a additional service that would check 2 things. It checked the lag, so has this data been around for a long time, and it checked the last time that we committed. So if those 2 things, if data's been around and we haven't committed in a while, then we'll go ahead and commit. And that never actually gets fired in production, but it's very important for development environments. So a little bit about our infrastructure. We have 3 brokers, 3 Kafka servers. So when I talk about scale, these 4 billion analytics reports that we get a day, the 1.9 terabytes of data that Flurry processes, all of that data goes through our Kafka servers, and we have 3 of them. So it can handle scale, and our utilization on these servers isn't even that high. So we have a lot of room to grow using Kafka. We have 400 partitions per broker, so 1,200 total partitions, and 325 consumers that read from those. And one of the important things to take away from this, a consumer might own 3 or 4 partitions. And if a consumer dies, that's okay, because you're talking about 4 out of 1,200 partitions. And so our data can still process and flow through the system with very little time for recovery. Whereas before, with our MapReduce work, if we had to kill a DLP job, that's 2 to 4 hours of processing, 500 million records. And that slows down system processing. So this was actually very important for us. And you see how Kafka's use of partitions and how consumers can only run one really helps you if things go down, and that can definitely happen. Currently, we have a single topic, so all of our agent reports go to this topic. All of our ad logs go to this topic, like impressions that come through our ads. So we monitor our Kafka servers. We use Yammer meters. And right now, we're using graphite. This is a graphite graph. We are investigating and will likely soon move to OpenTSDB. As you heard in the keynote, it has many advantages. We persist data forever, so you can have longer look-back periods. And it's also backed by HBase, so it'll scale a little bit better. But right now, graphite's been working pretty well. We measure things like the utilization of our servers. We measure things like the lag. If we have a lot of scripts built, so there's a tool that's native to Kafka. It's called the Consumer Offset Checker, and it basically lets you know if your lag or your consumers are progressing, or if data is building up. And so we wrote a script around this to check all 325 consumers, and if they're getting backed up or not progressing, we'll send an alert to our ops team so they can investigate. We have tools built around if a broker fails. So if a broker fails, again, we're using HDFS as an underlying store. So we basically say, okay, how much data has been processed? We can look at Zookeeper and see the last offset for those. And we just basically take the data from HDFS that hasn't been processed, load it back to our producers, and our producers will send that data to the available brokers. If a consumer fails, we basically kill all the tasks that they were doing. We will clear the logs, and finally we'll actually put it to sleep. We don't kill it immediately because we found consumers usually don't die. What happens is it's something like an HBase pause, and so it times out in Zookeeper. So we just put it to sleep, and if it, in 60 seconds, comes back, it can start over from the last commit it had in Zookeeper and process the data again. Now, one important thing to take away from this is because things can fail, because you don't commit after every log you process, it is very possible that you will reprocess logs that you've already processed. So your task that you're processing through Zookeeper have to be idempotent. That is, if you compute the same data multiple times, there are no side effects, there are no consequences. It is just as if you computed the data once. And that is very important in a system like this where failures can occur in a variety of places. So the next steps. Well, we are very, very excited about point 8 because point 8 provides replication. And so when that comes out, we won't have to have the HDFS layer. We'll be able to write directly to Kafka and not worry about this underlying store. We'll still use HDFS, but it won't have to go through this. The Kafka cluster will look something like this. From our previous example, you'll see that broker 1 will have a copy of partition 1 and partition 3, and broker 2 will have a copy of partition 0 and partition 2. What Kafka does is you will only ever write, if you're writing to partition 0, the producer will only ever write that data to broker 1. It will never write it to broker 2. Kafka will be responsible for replicating that data for you reliably to broker 2. So this is a huge improvement. It'll let us clean up a lot of code and just make it much more streamlined when we can do this. We want to extend the pipeline. So right now, as you saw, the Kafka part is the first part in the process, but we want to have a real-time portion of the system from start to finish. And of course, we'll always do MapReduce. And if you're wondering why we'll always do MapReduce, we have a lot of jobs that have to scan the entire table. Because take, for instance, our persona data, our segments. Personas could track that a user is a hardcore gamer, a business traveler, or first-time mom. But that's not always going to be the case. And so you have to compute this data over time and often look historically at data. And so we'll still use MapReduce for that, scales well, and those things don't actually need to be real time. However, something like new users. If you get a new user on your app, you really just need to increment a number. So this leads itself pretty well to a consumer producer system. So in infrastructure and setup where we want to go, we'd like to have multiple consumer groups that can all read from the same stream of data at the same time, but do different things. And so maybe incremental analytics, that new user you get, that can be one consumer group that's responsible for that. Our alerting system, that can be another consumer group that's pulling from the same stream of data, so really breaking down any dependencies in the process. We want to have multiple topics. So right now we have one topic, but we can have a topic that just handles analytics data. We can have a topic that handles our ad serving data. We can have a topic that handles our tracking information and budgetary information. And the real key to doing that gives you more flexibility with your infrastructure, because you can say, okay, I'm going to devote part of my cluster to just these topics. And that'll give you that kind of flexibility. So we're excited about these next steps. We think Kafka has done great for us, and we believe we can get it even faster, especially when 0.8 comes out. And I definitely encourage you all to use it if you're interested in real-time processing at scale. Thank you.